Hello, my name is Michal Edelstein, and I will present our work, ENIGMA, Evolutionary Non-Isometric Geometry Matching. This is a joint work with Daniela Zuz and Mirela Benchem. Let's start by explaining what is the problem of shape correspondence. Given two shapes represented as triangle meshes, our goal is to generate as output a correspondence, or a map, from M1 to M2. So given a point P on M1, we'd like to compute the corresponding point on M2. If we know this map for all the points on M1, we can use color to visualize this correspondence. Matching points are displayed in the same color. The goal is to compute the semantic correspondence between points on the shapes, so that the knee goes to the knee and so on. Shape correspondence or shape matching is a fundamental task in shape analysis. It has many applications such as texture and deformation transfer, shape interpolation, and more. The difficulty of the shape matching problem depends on which shapes we want to match. If the shapes are rigid, we know Euclidean distances are preserved, and the transformation between them is a rotation and a translation, and the problem is much easier. For matching non-rigid isometric shapes, like the same cat in different poses, the problem is harder, but in this case, geodesic distances are preserved, and we have a clear criterion for the quality of the map. In the general case, we want to find the correspondence between non-isometric shapes, meaning between shapes that have significant differences, but still belong to the same semantic class, so the correspondence is meaningful, like the giraffe and the horse. In this case, we don't have any prior knowledge that can lead to a clear criterion on the map. This is the problem our algorithm addresses. There is a large body of work on shape correspondence. Many approaches use user-provided landmarks or are data-driven. Our method, on the other hand, is fully automatic and requires only the two input shapes. We therefore focus a comparison with fully automatic methods. In this space, we compare two four state-of-the-art methods. The first two compute sparse correspondence between the shapes. The mapping preserves geodesic distances, which is good for isometries. The third one, BCICP, is based on the functional map framework. They iteratively switch between functional mappings and pointwise mapping, and the result is a dense map that isn't always locally accurate. The fourth is a genetic algorithm like ours, but their setting is very different from ours. They are also based on preserving geodesic distances and are intended for isometries. We can consider the shape correspondence problem as a two-step process. First, the global semantics of the matching is given by a sparse set of corresponding landmarks of salient points on both shapes. If this set is informative enough, it can be extended to a full dense map in a consistent and smooth way. The first problem is combinatorial, whereas the second problem is continuous. Many automatic shape correspondence methods address the first problem for isometric shapes, and there are many great semi-automatic methods that address the second step for both the isometric and non-isometric case. We propose to combine the step and leverage efficient algorithms for solving the second problem to generate a framework for solving the first. Meaning, our approach is to find the landmark correspondence that can be extended to the best dense map between the shapes. Since the problem is combinatorial in nature and the objective is nonlinear and non-convex, we use a genetic algorithm that allows us to optimize for it. Genetic algorithms were proposed in the 60s. They were inspired by natural selection. We have a population of solutions, and they are combined and mutated, so that with each iteration, the population improves. These algorithms are effective for our type of problem, challenging combinatorial optimization problems with many local minima. Now I'll talk about our pipeline. Our pipeline includes 3 steps. We receive 2 shapes as input. The first step is finding geometrically meaningful landmarks. The second step is finding the mapping between them, which we do using a genetic algorithm. The last step is a post-processing step to extract a smooth, dense map. We'll start with the first step, landmark computation. For each shape, the landmark computation is done separately, hence we have a different number of landmarks on each shape. In addition, only a subset of the landmarks matches. Our goal is to choose landmarks which facilitate such a partial match. Hence, our goals in computing the landmarks are: they should be informative so that they represent the shape, but also feasible so that a match can be found. We usually have about 10 to 30 landmarks depending on the class of the shapes. Note though that the number of landmarks is chosen automatically by the algorithm and no additional input is required from the user. The landmarks we compute are divided into 3 types, and usually matching landmarks originate from the same types. The exact details are given in the paper. The next step of our method and our main technical contribution is the computation of the partial landmark correspondence using a genetic algorithm. A genetic algorithm has the following steps. First, a population of candidate solutions is initialized. Then, the fitness of each solution, meaning its quality, is evaluated. Next, the fitter solutions are combined and mutated, and the new solutions are added to create a new generation of possible solutions. This process repeats until the algorithm converges to a satisfactory solution. When combining and mutating the solutions, the fitter individuals are selected from the current population for crossover when 2 solutions are combined to create new solutions, and for mutations where they undergo small changes with a low probability. We designed novel geometric genetic operators specifically for our problem. First, I'll talk about how we represent the solutions. Our population is a set of candidate solutions. Each solution is called a chromosome and represents a partial permutation. For example, the one we see here. Each chromosome is composed of genes, where each gene represents the match of a pair of landmarks. For example, the match of the landmarks on the nose. As an example, we can look at these 2 birds. The first one, on the left, has 5 landmarks, and the second, 4. The length of the chromosome is the amount of landmark on the first shape, and the values represent the matching landmarks on the second shape, or 0 if there isn't any. For a chromosome to be valid, it must be injective, meaning that no value except 0 can appear twice. The correct solution represents the desired semantic correspondence. Here, the 2 heads are matched, and the 2 tails are matched, and so on. The 5th landmark on the first shape has no matching landmark. The second chromosome is valid, but represents an incorrect match, because the head is mapped to the tail. The third is invalid, but is not injective, since 4 appears twice. For constructing the initial population of candidate solutions, we use a gene bank. For each landmark on M1, we find a set of landmarks on M2 that are a potential match and save them. We do it for all the landmarks on the first shape. The gene bank is built according to the landmark sources and the wave canal signature. It is used for the initialization and the crossover, but does not restrict the algorithm, meaning we also get genes that don't appear in the gene bank. Now I'll explain how we build the chromosome of the initial population, starting from the landmarks on each shape and the gene bank. We start with a random landmark on the first shape that has a good certainty, meaning up to 4 options in each gene bank. Its possible matches from the gene banks are displayed in magenta. We choose its matching randomly. I will point out that we consider the symmetric mapping as correct as well, if all the landmarks are mapped to their symmetric ones. Then we choose another landmark on the first shape. We take the closest unmatched landmark. To find its match, we choose an option from the landmark's gene bank that is close to the matched gene. In this case, the landmark on the right hand is selected. If there is no possible match from the gene bank, we will try to find a match from the landmarks that originated from the same method. If none are valid, we will leave the landmark unmatched and continue to the next one. After adding 2 more landmarks in the same way, the landmark on the chest has a few possible matches, 2 in the front and 2 more in the back, all close enough to the closest matched landmark, in green. In this case, a random landmark is selected. The next closest unmatched landmark has 2 matching options. Both are close to the closest matched landmark, yet the one under the right armpit was previously selected. Therefore, the landmark under the left armpit is chosen. After going through all the landmarks, the resulting chromosome is displayed. Since we want the initial population to be versatile, we erase a few of the matches to get a random size chromosome. We repeat the process of constructing chromosomes until we reach the required population size. The initial population contains many chromosomes that are incorrect or partially correct. For example, if we look at the chromosome we just built, in some areas, such as the arms, it represents the correct match, and in other areas, like the leg, the match is incorrect. So globally, the chromosome doesn't represent the correct correspondence, but it is locally correct on part of the shape. Since it is just a solution for the initial population, it is good enough. It will improve in later stages. After initializing the population, we need to evaluate the fitness of each chromosome. How should we define the fitness function? We need an objective function that will determine the quality of each solution. Our requirements of the fitness function are that it can be used for non-isometric matching, as this is our goal. We also need the computation to be fast, since every solution in every generation should be evaluated. In addition, the fitness function must be indicative. The global minima should be at the correct feature assignment, but we also need partially good matches to have a better fitness than bad matches. We want to find the landmark correspondence that can be extended to the best dense map between the shapes. We do it in two stages. First, we generate a dense map based on the landmarks using the functional map framework. We choose to use the functional map as it performs most computation in a reduced spectral basis and is therefore significantly faster. Then we evaluate the reversible elastic energy. This energy was recently used to generate high-quality dense map between non-isometric shapes when the landmarks are known. We only measure it, and it gives us a good evaluation for the quality of the mapping. To demonstrate the behavior of the fitness function, we show the fitness of a few chromosomes. The energy of the correct match is the lowest. A small change, like switching the legs, results in a higher energy. When all the landmarks are marked incorrectly, yet in a consistent way, the energy is even higher. And the highest energy is obtained when the landmarks are mapped incorrectly and inconsistently. Next, we have the genetic operators. After evaluating the fitness of the population, we combine and mutate the solutions. For that, we start with the selection. We want to select the fittest individuals, whose genes will be passed to the next generation. We use a fitness proportionate selection, where the fittest chromosomes have the best chances to be selected. It's like arranging the chromosomes on a roulette wheel. Each chromosome takes a part of the wheel based on its fitness value. The fitter the chromosome, the more chances it has of being selected. After the selection, we perform the crossover. This operator merges two input chromosomes into two new chromosomes. We need our crossover operator to produce partial permutations, and we also want it to be geometrically meaningful. Our crossover operator is therefore defined as follows. If we take two different chromosomes, the first with genes marked with spheres and the second with cubes, and combine them, we receive a child chromosome whose genes are marked according to their origin. Note that most genes in the top of the body are from the cubes chromosome, and most genes in the bottom from the spheres. Hence, the geometric partial match that existed in the parents is not broken during the crossover. Our operator uses similar techniques to the population initialization algorithm, and we refer to the paper for more info. In addition to the crossover, we also design new operators for different mutations that change the amount of corresponding landmarks and their values. Those occur with a low probability. After creating new chromosomes, we add them to the population. To do that, we take the fittest chromosomes from the original population and the fittest offspring and combine them to create a new population. By keeping the fittest chromosome from the original population, we guarantee that the energy of the fittest chromosome will not increase. We repeat this process until our algorithm converges. We stop when a maximum number of iterations has passed, or when the fittest chromosome remained the same for several iterations. Here we show the population evolution. The graph on the left shows the energy of the fetus chromosome and the mean energy of the population. Both decrease until convergence, indicating improvement throughout the generations. In this case, the algorithm converged because there was no improvement in the last generations. On the right, we show the fetus chromosome at different generations. In this case, the initialization is generally good, but the front legs are switched, whereas the back ones aren't, and the body isn't matched correctly as well. The match improves with each generation until reaching the correct correspondence. This concludes our genetic algorithm. Our output is the sparse correspondence of the landmark and the functional map based on that correspondence. As a post-processing step, we use the functional map as input to reversible harmonic maps to receive an accurate point-to-point map. Now I'll show a few results. We run our algorithm on two datasets, SHREK 7 that contains non-isometric shapes, as well as ground truth sparse correspondence between manually selected landmarks, and SHREK 19 that contains shapes of different topologies. Since the given sparse ground truth does not necessarily coincide with our computed landmarks, to quantitatively evaluate the results, we first perform the post-processing step to extract a pointwise map. We use the same post-processing for all methods. The x-axis is the geodesic distance between the ground truth correspondence and the computed correspondence. The y-axis is the percentage of correspondences with less than x error. Higher is better. Our method outperforms the other methods. Here you can see one example of the comparison of our resulting landmarks and functional map with other methods. In this case, both tight relaxation and GA plus AS switch the legs and the head of the bears. DS++ result is also incorrect, easily visible on the belly of the bear. Our method, on the other hand, yields a semantically correct correspondence. We also compare our results using texture transfer after applying the same post-processing for all methods. Note that both tight relaxation and DS++ have problem in the tail. GA plus AS switches the head and the tail and has a problem with the fin, and BCICP maps the front of the fish incorrectly. Our method produces good results and outperforms these approaches. Our method is applicable to shapes of any genus and can also match between shapes of different topologies, as seen here. In the paper, we have additional results showing the stability of our algorithm as well as an ablation study. To summarize, we provide a fully automatic method for non-isometric shape correspondence. We split the problem into two parts and compute the sparse landmark correspondence that can be extended to the best dense map between the shapes. To solve this combinatorial optimization problem, we use a genetic algorithm with geometrically guided operators we designed. Our method is not limited by the topology of the shapes and achieves very good results. Thank you for listening.